Welcome to this course on convex optimization once again, and to this parallel little sub course which I am calling the pleasures of linear programming, because this is something which we can handle so well and tell you a lot of things. There is beautiful convex geometrical structures involved. So, in the last class or the last lecture, we had shown that every BFS or basic feasible solution of a linear programming problem in its standard form can be corresponded with a vertex, that is, that corresponds to a vertex on the convex polyhedron and vice versa. Now, what we are going to show that, so every vertex is corresponding to some BFS. What we are going to now show that if I know beforehand that my original problem has a solution or has a lower bound is immediately guaranteed by the feasibility of the dual which we had learnt by through weak duality, which we had learnt earlier. So, once I have a lower bound, I can prove that it is a solution, and that solution will be one of the vertices. But in order to prove such a fact, we need to know certain more facts. So, we recall certain things. For example, we recall polyhedral sets. Polyhedral sets are very important, because polyhedral sets are the basic structure of a linear problem, because a linear problem is nothing but minimization of a function, linear function, over a polyhedral set. So, we come and have a recollection of polyhedral sets. So, a polyhedral set is the intersection of the half spaces, and it could be bounded or it could be unbounded. It is bounded, for example, here. So, any bounded polyhedral set which is also called a polytope can be written as a convex hull of its vertices. So, you have V1, V2, V3, V4, V5. In this case, this is the convex hull of these 5 vertices. But there could be unbounded polyhedral sets too, which has a vertex, but this whole thing is not a convex hull of this vertex naturally. So, for example, Rn plus is an unbounded polyhedral set. Now, we will go into the notion of what is called a polyhedral cone. So, a polyhedral cone C can be written as the set of all x in Rn such that ai x is less than equal to 0, that is bi is equal to 0. Okay. A polyhedral cone, for example, is like this. If you take R2 plus or Rn plus, R2 plus is a cone and is a polyhedral at the same time. So, R2 plus is an example of a polyhedral cone. Similarly, Rn plus is also an example of a polyhedral cone. Now, you can easily prove that set C is a cone. Prove on the other hand, there is also another definition which came up in literature as a finitely generated cone. Let me just draw a few more polyhedral cones. In 3D, for example, if I take this is an example of a polyhedral cone, because any point you see these faces of the sides of the cone are actually hyperplanes which are passing through 0. So, this is an example of a polyhedral cone. This is a polyhedral cone. Of course, it is coming up like this. So, going up to infinity, but we do not bother about that in the drawing. But a very important cone like this, like the Lorentz cone in 3 dimensions. Also called the second order cone. This cone, sorry, I will write it as a Lorentz cone L. has a huge impact in something called second order cone programming, which we will come later on. So, if I take L here and let me describe this, it consists of all x 1, x 2, x 3 such that root of x 1 square plus x 2 square is less than x 3, where x 3 is greater than equal to 0. So, this is a non polyhedral cone, because here I have quadratic inequality, not a linear inequality. So, it is not a polyhedral cone. So, this is non polyhedral. In fact, the set of all positive semi-definite matrices Sn plus can be mapped in a natural way to this cone. So, in that way many problems which are actually semi-definite programming problem can be posed as second order conic problem, about which we will come in detail later when we study semi-definite programming. So, this is an example of a non polyhedral cone. But if this being a convex cone, if you look at any point here in this polyhedral cone, you will observe that any point can be written as a positive linear combination of these 1, 2, 3 vectors, right. So, these vectors are essentially called the generators of the cone, and that led to the definition of a notion called finitely generated cone. A cone C is finitely generated if any element z in C can be written as z is equal to summation lambda I a I say m, where lambda is greater than or equal to 0 and a1 a2 am are given. So, this a1 a2 am, these things are called generators of the cone. Now, the interesting fact, or a very important fact in convex geometry, is the following: a cone C is polyhedral if and only if it is finitely generated, and that is the fascinating thing. Now, also I would like to recall before you a very familiar notion of a cone generated by a set A. This consists of all the points x such that x is equal to lambda z, where z is an element of A, and lambda of course is greater than or equal to 0. This is called the cone generated by A. Of course, you can also define the convex cone generated by A. So, for example, if you take these two lines only and call these two lines, the union of these two lines as A, then you can, these two lines, this to fork is what is the cone generated by A, but the convex cone generated by A is the convex hull of the cone generated by A. So, basically, I will say like this: convex cone generated by A, generated by A. Now, if you take a full dimensional convex set like this, then you are always bound to get a convex cone. When you any cone that is generated like this, any cone that is generated in this fashion has to be a convex cone. So, these notions are slightly different, and now why are we all doing this? Because once we have this idea, we would be able to make a interesting representation of any polyhedral set, and this representation can be carried over to the feasible set of a linear programming problem, and that would lead to what we want at the end. My next important result is representation of a polyhedral set. Now, once I want to, how do I represent it? The interesting fact is that any polyhedral set can be represented as the vectorial sum of two sets. One of them is a convex polytope and another is a finitely generated cone. So, the cone takes in the unbounded thing. So, when you are talking about just the polytope, then this cone is nothing but the 0 vector. So, if P is any, say P is a polyhedral set, obviously it is convex, which I am not writing, polyhedral set, then P can be written as P hat plus D, where P hat is a polytope, which is another name for bounded polyhedron, and this is a finitely generated cone. So, going back, these AIs are called generators of this cone. So, sometimes it is convenient to write a finitely generated cone as a cone generated by the vectors A1, A2, AM. M could be any number, it is not fixed, some fixed number. Now, which means that there would exist vectors V I from 1 to k and d j, say j from 1 to L, such that P is the convex hull. So, any polytope can be represented as the convex hull of its vertices. So, V 1 they suppose it has k vertices, then it is V 1, V 2, V k plus the finitely generated cone generated by the generators d 1, d 2, d L. This fact somehow proves pivotal. Now, you might ask me what is the proof of this? We are not getting into the proof of this, because to prove this it would force us to prove the fact that every polyhedral cone is finitely generated and vice versa, which is a time taking process, and we will not get into this, because again we have to remind you that those who are in mathematics, they can go and we can tell you a book which you can read. So, if you want to know the proof and the detail of this, I would suggest you two books. Borwin and Lewis, which I had already mentioned earlier, convex analysis and nonlinear optimization. And the second book is Foundations of Optimization by Osman Guler, a recent one. Now, this is by Springer, this is also by Springer. So, the publisher is Springer. Costly books, by the way, do not worry. None of them has an Indian edition so far. So, you need to go to the libraries. Now, once I know this, how can I use it to prove what I intend to prove? That once a linear programming problem LP has a lower bound, this is just fascinating. It will always have a minimizer. Now, what I would do instead of the proof I give here is due to Osman Guler from Foundations of Optimization, and I would like to state that the proof is given for a optimization linear optimization problem in a much more different form than you have. So, what Osman Guler has done is to consider a problem of this form. he has not put in any restrictions on the variable. So, as the most general form with any inequality. So, I can write this again into an equivalent form if each A I is a vector representing the rows of A, and I can write this as A is same M cross N matrix and all those things which you all know quite well. Now, we will assume for this particular problem LP 1 I am calling it, I do not know why I am calling it 1, but just calling it 1. So, LP 1, let me take this problem LP 1. So, let LP 1 have a lower bound. Now, look this set C here, this is a polyhedral set. Now, it is very important to understand that this set could be bounded, could be unbounded. If it is bounded, it is fine. If it is not bounded, then we have to use the representation that we have just seen. Now, LP has a lower bound. So, let the lower bound is M. Which means that is C transpose X is less than equal to M for all X in C. That is exactly what is the precise meaning of the lower bound. Okay. Now, if that is the case, let me put now C by the previous result, this result can be decomposed in this way. I am just taking this decomposition. So, C can be written as convex hull of the vertices V1, V2, Vk plus the finitely generated cone generated by D1, D2, DL. Now, once I know this, what could I possibly do? So, if I take the convex hull of V1, so any element here, take any element Z here, Z in C, this can be written as lambda I V I is equal to 1 to k plus mu j dj, j is equal to 1 to L, where your summation lambda I equal to 1 to k is 1 and lambda I is obviously lying between 1 and 0, that is a convex combination, and mu j's are greater than equal to 0 for all j equal to 1 to L. So, that is exactly what you want. So, any j can be represented, there will be some lambda, some mu j's, and okay, any j can be represented like this. Now, what would happen? Suppose I take lambda equal to 1, say lambda 1 equal to 1 and put all the other lambdas to be 0, and I take sum for some j. So, take a j and corresponding first take corresponding to that j put mu j as some number and put all the other mu j's to be 0. Then what from here what can I conclude? That V1, you could take any I also. So, I am just taking with V1 for simplicity. V1 plus T of dj for all T and all j means every. So, what you do? You first take one j, say D1, say put, so V1 plus take any fixed T whatever you want, whatever, say V1 plus T of D1 is element of C, V1 plus T of D2 is element of C and so on. So, this is an element of C for all T bigger than equal to 0 and for all j is equal to all j running from 1 to L. So, this is simple, just you have to note this representation, put the proper values, putting here basically putting all lambda is equal to 0 except lambda 1, which you put 1, and here take any t whatever you want, take any j you want, the remaining all you push to 0, and then by this is of course an element of C just by this representation. Now, once I know this, what can I do? Now, because this is in C, by my very definition of bounded the bound M, so this is what I have, what I would have. This simply just go back and recollect this definition. This is the meaning of the lower bound. Now, I can write this as C of V 1 plus T times C of d j is bigger than equal to M. Okay. Now, as t tends to infinity, now let me see what would happen as t tends to infinity. Now, if C of d j, if one of them is less than 0, negative, and I can make t go towards infinity. So, there will be a minus component which will become bigger and bigger and bigger and bigger. So, finally, it will just overpower this C V 1 and can go into completely into the minus domain, and can the value can continue to decrease, the value of this will continue to go down because C V 1 is fixed, and it can go just below M. So, as t tends to infinity, because of this bound, it would imply that C of d j has to be greater than equal to 0 for all j. This is what I have. Now, once I know this fact, I can look into the original problem in a slightly different way. So, I have this problem. So, I can now write this problem as following. Now, I have any x here is belonging to this set, which I have written, and any element in this particular set C is represented like this. So, I can have that L P 1 can be equivalently written as this, where subject to, of course, lambda I is greater than equal to 0 for I equal to 1 to k, mu j is greater than equal to 0 for j equal to 1 to L, and the summation that must be equal to 1. So, the problem L P 1 can be equivalently written like this. Now, knowing that this is greater than equal to 0, what should I get? I should get the following. I should get, because if what is happening is the following. Now, if you look at this, to this quantity lambda is Ci, we have added a positive quantity, non-negative quantity. So, this quantity is actually bigger than the previous term. So, which means that summation I is equal to 1 to k lambda I C V I plus summation j is equal to 1 to L mu j C d j, because now this is a non-negative quantity, then because if I add some non-negative quantity to a given number, I actually increase that number. So, this whole thing must be bigger than summation I is equal to 1 to k lambda I C V I. Now, I will ask you to prove the following. show as homework the following, show as homework the following. The minimum value obtained by solving this problem so this minimizing this is same as minimizing very important here the minima is on two variables. So, here observe the minima here is transformed from x to these two variables lambda i's and mu i's, lambda in R k plus lambda in R k and this is in R L. So, basically we are changing over from minimization on x to minimization on these multipliers. So, just let me, oh my god. So, now what I can prove because of this fact and because of this is greater than equal to 0, that this thing is nothing but now this is quite intuitive because this quantity is nothing but this quantity with putting mu j is equal to 0 here. So, I can always put mu j is equal to 0 because mu j's are greater than equal to 0, it is your choice whether you put it equal to 0 or greater than equal to 0, it is up to you. Now, hence whatever way we try, the functional value has to be always bigger than this and which is also one of the functional values. So, the minimum achieved by minimizing these functional values will be obviously less than this one. So, but again the fact that we are minimizing over this objective would actually bring in this. It is just a simple writing down thing. Using this, put the minima on both sides, then noting that okay, that the minima of this has to be less than the minima of this, has to be less than this. For whatever lambda I, this has to be less than equal to this. So, the minimum of this has to be less than equal to this for whatever lambda I. So, again you minimize, so you get an equality, but so I will not do this work for you, you are supposed to do this equality. First note, once I have this, I can operate minima on lambda mu, minima on lambda mu. Here mu is irrelevant, so the minimum of this is bigger than the minimum of this, fine. But now, for whatever lambda mu you take, the minimum over this, the infimum value is less than equal to the infimum value of this, is less than equal to this, because this is nothing but a particular feasible choice, lambda i's, some lambda i's and mu j's are all 0. So, minimum value of this is obviously less than this. The minimum value exists, the infimum exists because we have assumed a lower bound of LP1. So, but then for whatever lambda I choose combination, the minimum value of this is always less than this. So, the minimum over lambda is always bigger than the minimum over this and hence these two are equal, which is absolutely simple. Now, the question is noting that summation lambda equal to 1, show as homework this is nothing but minimum of C V I is equal to 1 2. So, you are, this is exactly linear programming's game, that you are computing the objective function value at the vertex and taking the minimum one. So, show this equality as homework. You see, just try it out, it is going to be fun and you will see that mathematics really works, and that is why it is so beautiful. So, what I have proved, that the minimum value of LP1, because now here I have only finite number of them m. So, one of the CVI values, say CVJ is the minimum, say this value is equal to CVJ, say or CV, say let me take CVR for some R element of 1 to m, which is obviously true. Just you have finite number of finite some few numbers, you have to choose the minimum. So, you chose the minimum. So, what happened? The minimum of LP1, which is this, is obtained at this, is actually this value where VR is nothing but a vertex. So, for an LP, so for LP1, so in general I am writing for our LP problem, our LP in the standard form. So, for an LP, optima or the minima in this case is obtained at the vertex, obtained at a vertex. Now, these vertices V1, VR, these are also elements of the set C, but these are vertices of a polyhedral cone. So, actually how do you represent a polyhedral set? Basically, you take the vertex of the polyhedral sets and make a, you take the vertex of the polyhedron and make a polytope taking the convex hull, and then add to it the finitely generated cone. So, these are actually vertices of the original polyhedra. Naturally, these are actually vertices of the original polyhedra. So, once you know this, so for an LP, optima or the minimum is obtained at a vertex, and thus every optimum or every minimum is a BFS by the previous stage result. Now, before I end this today's lecture, and after the next lecture we will start with simplex method, which we will do in more of the nonlinear programming style. Now, what I have done, I have proved this fact for LP1. Now, I have something more to tell you. Can you prove this fact for LP? Prove the above result for LP. For the standard form. So, here LP, the setting of C would change, is the same thing, you just do not have to worry about. Homework, small modifications are needed, which you should try to carry out because it will be fun, and maybe a good idea is that okay, these, when you take these actually are vertices of C, and can you prove that these are actually vertices of C. So, proving this to be vertices of C is not a very bad idea, that actually works, that these are not just some arbitrary points you have taken which are vertices of this polyhedron, but this is also, they are also vertices of C. So, I can show that you cannot have two elements which are different from each other and whose convex combination with lambda between 0 and 1 would give you V1 or V2 or V3 or Vk. So, that is something very important. So, if that is so, then they are, those things are all equal. So, that can be done quite easily, quite easily. So, let us not get too much bogged with that, but it is a good idea to try it out, that these are also actually vertices of the set C. So, we have proved quite a bit of stuff today, and tomorrow's class or the next class would be on the simplex method. So, with this I would like to end today's lecture, and because if I want to start simplex method, we will get into too much complications today and we will not be able to finish the foundations, because the foundations of simplex method are quite heavy to lay down, and unless I do it, start and complete it, is meaningless to just start and leave it off for today. So, it will be good if we start it in a separate lecture. So, what we have now is quite a broad view of optimization. We have learned about Lagrange multipliers, saddle point conditions, duality theory, convex analysis, as well as a focus on as well as what we are doing now, focusing on the most important class of problems, the semi definite programming problem and the linear programming problem. The semi definite programming problem is so powerful, which has extremely important applications at present into understanding quadratic programming, non-convex quadratic problems, in understanding polynomial optimization problems. So, we would thus focus ourselves on these two classes of problems. So, that would lead us to a much better understanding of modern convex optimization theory, because modern convex optimization theory is essentially the story of semi definite programming, though there are many other things which like bundle methods and all those things. So, whatever we find time, we will try to push into in these 40 lectures. One can think of an advanced set of lectures later on, but let us just concentrate on these two important aspects and do them in detail, so that especially the engineering people here who are listening to these lectures should know that LP and semi definite programming, SDP or semi definite programming per se, is extremely important from the point of view of applications in engineering, extremely important. I think so, it is important on my part to really concentrate on these two aspects of the subject. Thank you very much.